So that means the section is neutral axis, normal. Okay, after deformation, this neutral axis, still normal. Okay. It's A, for example, B, A, B. Okay. Yeah. This neutral axis. Right. And this is a rotation dw dx, and this is a dv du dx dz. Sorry, it's dz du dz dw dx. Sorry. Okay, because this is a dx, but here is du. Okay, the angle, same. So this angle is same as this angle. Okay. Yeah. The two are the same. Okay. The w dx. This is the w. This is dx. This is the dz. This is du. Okay. Both are tangent theta. Tangent theta. Okay. And you can see the point original at this location with a z coordinate. For example, this point P. And after deformation, it moved to here, P prime. Okay? So this displacement, P prime, the displacement U is equal to minus Z times dw dx. For the positive rotation, will cause a positive Z have a negative U. Do you know what I mean? That's why this negative sign comes. So this is U equal to minus. So that means for a negative coordinate Z, it has a positive U. Okay? If you put a negative Z, you get a positive horizontal displacement U. Okay? So this is a very important result. Due to this, we simplify the whole analysis. Okay? Yeah. And you can see, so for the U at x, z is equal to minus. So this point, P at x, z equal to the diffraction at x, the first derivative, okay, times is z coordinate. You can get displacement, horizontal displacement U. Okay, so this is the key of the beam theory. All right. Yeah. Then, all right, and we also know from elasticity, we say the epsilon ij, the straight tensor, is half partial ui partial xj plus partial uj partial xi. Okay, I didn't prove this for you, but this is you take it as you know it, right? Okay, and for example, epsilon xx is equal to epsilon 1 will be half partial u1 partial x1 plus partial u1 partial x1. Okay, so there will be half partial u1 partial x1. Okay, In Bing's theory, our U1 is equal to U. Our X1 equal to X. So epsilon Xx equal to partial U, partial X. In Bing's theory. Right? Okay. So we apply this. So my strand X, horizontal strand at XZ coordinate equal to partial U, partial X equal to minus Z. Actually, okay, partial U, partial X. That'll be dW dx squared. Okay. And we say this is a Z times a minus dW dx squared. And we will show you later this is equal to Z curvature. So this is curvature. Okay, Z curvature. And why we define this minus dW squared dx squared is equal to positive curvature. I'll show you later. Okay. Yeah. Yeah. Okay. For example, in our system, like X and W like this, okay? And our bending moment will like this. Our positive bending moment is like this, right? And we define this shape is positive curvature, okay? All right? But in this coordinate system, this will be positive curvature. This shape, okay, I'm saying, in this system, this shape represents the dW dx squared. For this system, dW, positive dW squared dW, this like this shape. Okay? So this shape will be minus dW dx squared. Right? So that's why we say curvature equal to minus dW dx squared. Okay? So if some guy, they like the W upward, so be careful, okay? Be careful of the system. You should derive from beginning to double check it. Understand what I mean? And in mathematics theory, what definition of curvature? In the calculus of geometry, the curvature means the ds. Okay. The theta changing. For example, this is for theta, and this is theta plus d theta. So this d theta things is negative, right? Reduce. But anyway, the theta change per unit arc length. If you along the curve, the tangent of the curve, the angle changing, is called the curvature. This is a definition of curvature. Is the theta change per unit s. So this is a fundamental definition of curvature. Okay. And our theta here is what? For a straight line, our theta is, we use a dw dx theta. Okay? Our ds is dz dx. So, okay? So that's why the order is dw dx squared. Yeah. That's why. All right? So if you do some nonlinear beam or curved beam, maybe you should go back to this fundamental nonlinear geometric theory. Okay? So in our undergraduate mathematics 2, we talk a lot about vector, right? And the vector calculus. Okay? About the curvature, the line, moving space, corollary, acceleration, no things. Remember? Everything will come back if you go back to nonlinear things. Yeah. But vector is very important in mechanics. Yeah. Okay, let's introduce this curvature concept and strength from another way. Right?